In this video, we will discuss molecular representations, so ways to draw or represent molecules, and in organic chemistry, that's mostly visual, and functional groups. So functional groups are the basis of one of the most important types of patterns that we need to start to see so that we can predict chemical and physical properties of molecules. If you're scared of organic chemistry because you don't want to memorize, then you need to memorize functional groups so that you don't feel so overwhelmed in the future. So we can minimize our total memorization by learning functional groups now. Let's get started. Our learning goals for today are to be able to convert between bond line skeletal structures and complete Lewis structures, to define functional groups, to identify and name common functional groups in organic molecules. And again, this is very important because it will give us a framework upon which to predict physical and chemical properties. And finally, to classify a biomolecule as a protein, carbohydrate, or nucleic acid based on functional groups. Keyword for today. Let's begin by reviewing the bonding that occurs in organic molecules. What I want you to do is use this data to predict the carbon-carbon bond lengths in these two molecules. We aren't in the same room together, so I can't ask you what you predicted. However, this is a pretty typical answer that I see or hear in class. And this is totally reasonable, so if you predicted this, good, good. We can see that molecules A and B seem to have three types of bonds. They seem to have single bonds, which we would predict to be consistent with a typical single bond length of 154 picometers. These two molecules also seem to have between them a double bond, and the double bond we would predict to have a length consistent with that of a carbon-carbon double bond of 134 picometers. In the molecule B, it has a triple bond, and we would expect the triple bond to have a length of 120 picometers. So these are our predictions. Just like we did in the last lesson, we could look up X-ray crystal data for these molecules, where someone has actually measured the bond lengths. For molecule B, we would be correct in our predictions. That carbon-carbon triple bond has a bond length of 120 picometers. The single bonds have a bond length of 154 picometers. This data is a nice demonstration of what we learned in the previous lecture, that as more electrons are shared between the carbon atoms, going from 2 shared electrons in a single bond, 4 in a double bond, and 6 in a triple bond, the bond lengths become shorter and the bond strength becomes stronger. Although our predictions for molecule A make sense, they turn out to be inconsistent with the data. Let's try to understand why that is now. For molecule A, the X-ray crystal data suggests that all 6 of these carbon-carbon bonds, every single one, all 6, I'm just going to point arrows to 3 of those bonds, but all 6 carbon-carbon bonds have the same bond length of about 140 picometers. Wait, what? What's going on? So the observation is not consistent with the prediction. Why do you think that is? What are we forgetting here? Yes, we're forgetting that this drawing of molecule A does not completely describe the molecule. This molecule can be described by 2 resonance structures. Wow, this is a really ugly drawing. Thank goodness we're not going to be drawing complete Lewis structures for much longer. So this other resonance structure, this other arrangement of the pi bonds, so I've shifted the pi bonds over, right? If we want to draw those curved arrows to show how the electrons move, well, why can't this double bond be here? Why can't this double bond be here? End up right there. Why can't this double bond right here? Why can't those electrons be shared here and end up there? Well, they can. And both of those structures represent what the molecule looks like. The real molecule is somewhere in between these 2 equivalent resonance structures. So all 6 of those carbon-carbon bonds are somewhere in between a single and a double bond. often you see the structure of benzene drawn like this, or the double bonds are shown as a circle, because the electrons shared in those double bonds are actually shared between all 6 carbon atoms at all times. Whoa, how can we know that? Well, we know that from the 2 resonance structures, and it is reflected in the observed bond lengths. The observation that all 6 carbon-carbon bonds have the same length at 140 picometers, which is somewhere in between that of a single and a double bond, and they have the same bond length at all times. So clearly we know that neither of these individual resonance structures describe the molecule very well. The molecule is in fact a composite, and it is described by this exciting drawing, but don't worry, you don't need to draw it like this. You will recognize when you see this molecule, molecule A, it's called benzene. What you need to recognize is the pattern. So let me redraw it one more time so that we can recognize the pattern that allows us to know that, well, when you draw this molecule, you need to consider 2 resonance structures that describe it, because it's not fully described by this one. So the pattern that you want to recognize here is the adjacent pi bonds. When there are adjacent pi bonds, you need to look out for resonance structures. Let me show you where that is. That's in our previous lecture. So it's in the bonding in organic compounds lecture. All the way at the end, we looked at 4 examples of molecules which are best described by resonance structures. And then we described the patterns in each of these that are represented by each of these molecules. So here are the 4 patterns. So that is what I'm referring to here. We have to start recognizing these patterns. All right, that was fun. So let's make sure we understand here. We discussed these examples so that we could review that as more electrons are shared between 2 carbons, as you go from a single bond to a double bond to a triple bond, the bonds get shorter and stronger. Second, we reviewed that when a molecule can be described by resonance structures, we need to consider them when we are trying to assign the bond length. When we first predicted the bond lengths for molecule A, we thought it might be simple. We thought that it had single bonds and that it had double bonds. We thought that the single bonds would be consistent with 154 picometers, and we thought the double bonds might be consistent with 134 picometers, the typical double bond length. But we were wrong, and we were wrong because molecule A is not simply described by this structure. It's described by both of these structures, and they are equivalent. And so the real molecule is some composite, right? Somewhere in between, where all the carbons are making some sort of double bonding interaction at all times. And that is why it is observed by experimental data that all 6 carbon-carbon bond lengths are exactly the same, 140 picometers, which is in between a single bond and a double bond length. You may have noticed that during this discussion, I subconsciously fell into my habits as an organic chemist, and I drew molecule A like this. And you may have wondered, where did all the carbon atoms go? Well, it was a lot easier when I drew it like this. So that transitions us into our topic for today, our first topic for today, which is there an easier way to draw these molecules A and B? And the answer to that is yes, there is an easier way. So when we draw out the Lewis structure, you can time me if you want. I'll talk while I'm doing it, but it takes some time, right? Draw out the complete Lewis structure. And now think about what organic molecules are made out of. They're made out of carbon and hydrogen and maybe some other elements. So think about all the carbon atoms that I have to draw every time I just draw a complete Lewis structure. What if I could imply them? And so we can imply them, and there is a system for that, which we will discuss right now. Done. I drew it. Carbon and hydrogen atoms implied. So yes, there is an easier way to communicate these structures, and let's go ahead and learn that now. Different structural representations give us different amounts of information. For example, you have encountered molecular formulas in general chemistry quite often. Molecular formulas tell us the types of atoms, their elemental identity, and the number of each type of atom. that make up that compound. However, molecular formulas don't tell us very much about how, or anything actually, about how the atoms are connected. So if I asked you to draw me a Lewis structure for that molecule, there are many different correct answers. You could draw a Lewis structure that looks like this. You could draw a Lewis structure that looks like this. And I could keep doing this all day, or at least for a few minutes longer. And don't worry, I'm not going to. So what can you learn from the fact that I can't figure out the connectivity of the atoms from the molecular formula? Yeah, we're going to need representations that tell us about this structure, because right now we don't know what the structure is. Now we can move on to a condensed structural formula. It looks a lot like a molecular formula, but it tells us about the connectivity of the atoms. CH3,2CHOH is C3H8O. But writing it out this way lets me know that there are two CH3 units bonded to a carbon atom, which is also bonded to a hydrogen, which is bonded to an OH. So we can draw out the Lewis structure from that. Yeah, we hadn't even considered this possibility yet. Now we know from the condensed structural formula that neither of our first guesses were correct. It's actually this molecule, this Lewis structure, which will have totally different properties from the two at the top of the page. So thank goodness for the condensed structural formula. Now let me lead you through one more time how I figured this out. So there are two CH3s connected to a carbon. That's this carbon, which is also bonded to this hydrogen, which is also bonded to the oxygen and the other hydrogen. And then I put in the lone pairs and follow all the other rules that we know. And sometimes you'll encounter what's called a partially condensed structural formula. The partially condensed structural formula will still show some of the bonds, it just doesn't show all of them. So for this particular molecule, the partially condensed structural formula might look a bit like this. The partially condensed structural formula shows some bonds, but not all of them. You can see the CH3 units and the OH, they're condensed relative to the complete Lewis structure, which is what I drew right here when I used the condensed structural formula to figure it out. So let's move it to where it belongs. A complete Lewis structure shows us all valence electrons. So it shows all bonding electrons, all non-bonding electrons, aka lone pairs, and all atoms. However, it took me a while to write this out, right? And as we mentioned before, there's so many carbon atoms in organic molecules. We like to just imply the carbon and the hydrogen atoms so that we don't have to take so much time drawing things out. And actually, you'll see when they're implied, it's easier to see the other parts of the molecule that are responsible for the physical and chemical properties often. So let's write out the bond line structure for this molecule. It's called isopropanol or isopropyl alcohol. So it's in rubbing alcohol. Now on a bond line structure, the carbon atoms are implied at each end and bend. You'll see what I mean in a minute, with enough hydrogens for a complete octet on each carbon atom. The bond line structure of isopropanol would look like this. Wow, that took me I don't know how long. Wow, that took no time at all to write. Then it's much more efficient, and I clearly see the OH part, which is going to be an important part of the molecule. All right, how did I do that? Well, I said each end and bend is an implied carbon atom. So here's that end is that carbon atom. This bend is the central carbon atom. And then this end is that carbon atom. And we can arbitrarily number these carbons 1, 2, 3. It is implied that carbon 2 has that one hydrogen atom. That hydrogen atom on carbon 2 is implied. How do you know there's a one hydrogen atom? Well, carbon 2 is making 1, 2, 3 bonds that you can see. That means it must make one more bond to a hydrogen atom in order to have a complete octet. So if you're not watching me draw for this part, I would, because I'm drawing and I'm erasing to keep the slide as clean as possible. So much of what you do today might just be watching me draw. And that's because your goal is to learn how to draw like I do. Like that's one of your goals by the end of this semester. Because through these drawings, we communicate chemical knowledge to one another. You'll also notice that the lone pairs on oxygen are implied as well. I did not show them. So you might draw them in for a while until you get used to them being there, get used to just knowing, oh, there's 2 lone pairs on that oxygen. Until you get used to that, you might draw those implied lone pairs in. Speaking of getting used to this, let's try some practice problems. Take a minute, pause, and draw the bond line structures for each of these molecules. So here's a complete Lewis structure. I want you to draw the bond line structure for that molecule. Another word for bond line is skeletal, and I'll probably use both terms. So this representation is where the carbons and hydrogens are implied. And use this condensed structural formula and draw the bond line structure for that molecule as well. All right, ready, set, pause, and go. It's your last chance. Pause. Please, you need to try this yourself. So there are many different strategies for solving these problems, and I'm just going to demonstrate one right now. I'm going to just see how many carbon atoms are in a chain, and then I'm going to draw that chain. So I need a 6-carbon chain. 1, 2, 3, 4, 5, 6. Great. Now I can see on carbon 2, there is this CH3 group. So that's just going to be one line coming off of carbon 2. And maybe I'll put my numbers here as well. So 1, 2, 3, 4, 5, 6. Carbon 2 has that one CH3 group coming off of it, and so there it is. Carbon 5, on the other hand, it has 2 CH3 groups coming off of it. So let's put 2 CH3 groups. And then we're all set, and we can check our work. Problem B looks a little bit harder, so maybe I'll take a different approach. I can definitely see I have a double bond between 2 carbons, so maybe I'll just draw that in first. So let's draw a double bond. And perhaps I should number my carbons as well. I'll number them carbons 1 and 2. On carbon 1, I can see there are 2 CH3 groups. So let's draw them. 1 of them, 2 of them. Off carbon 2, there is a CH2. There's at least one more carbon. We'll call that carbon 3. And then it says CH2. So I'll just draw those H's for a moment. And then what you can see, and then these H's are these right here. What you can see is that carbon number 3, it's only going to need one more bond. And that's going to be the bond to this oxygen. All right, so I feel good now. I feel like I know what I'm doing. I'll erase those hydrogens because they should be implied. And then now off of this oxygen, which I'm going to go ahead and number because that'll help me out. So that's atom number 4. There's another carbon, atom 5, and then another oxygen. So atom 5 here is a CH2. Let me put those H's just so I can make sure everything looks good to me. And then atom 6 is another oxygen. Okay, that feels good because that carbon atom, carbon number 5, it has 5 bonds to it. So I think that I drew it correctly. And then on atom 6, that oxygen, there's an OH. In skeletal structures, bond line structures, we don't usually show the lone pairs. Now, you might show the lone pairs for a while just because you need to, right? Because you don't, right now you're just getting used to remembering that an oxygen should have 2 bonds and 2 lone pairs. So you might draw those on there. That's fine. You might just do that the first thing when you start looking at a molecule. But technically, skeletal structures have lone pairs implied. Let's discuss some tips for drawing skeletal structures correctly. So again, every end or bend is an implied carbon atom with enough hydrogens for an octet. For example, we could draw this skeletal structure. The molecular formula for this molecule is C4H10. And that is because this carbon on the end, carbon 1, it has 3 implied hydrogens. It's a CH3. How do I know? It's making 1 bond to a carbon atom, so it must be making 3 bonds to hydrogen. Carbon 2, that's a CH2. Because it's making 2 bonds to carbons, it must be making 2 bonds to hydrogens that are implied. Same for CH3, and then CH4 is also a methyl CH3. It's making 1 bond to another carbon, so the 3 additional bonds must be to hydrogen. Add all of that up, and you do get C4H10. So each end or bend is an implied carbon atom with enough hydrogens for an octet. However, if you write out carbon, if you write C, the H's are no longer implied. So you cannot say, I'm just going to show that carbon at the end. No, you cannot do that. Now, you might want to write out a carbon atom for some reason. I do it sometimes. So if you write a C, you need to explicitly indicate how many hydrogens are bonded to it. So this would be okay. Tip number 2, all heteroatoms must be labeled. So here on the previous slide, I labeled the oxygen. Heteroatoms mean non-carbon, non-hydrogen atoms. So for example, oxygen, nitrogen, chlorine, etc. Anything that's not carbon and not hydrogen, it must be labeled. 3, related to that, you must show all hydrogens for heteroatoms. So you would not, for example, draw a structure like this. That's not right. What you need to draw the structure as, if there is a hydrogen on that oxygen, you need to show it. You need to write it out, OH. So that would be correct. Now, number 4, should you show the lone pairs on heteroatoms? Technically, they're not included in skeletal structures. And if you're doing online homework, then you need to read your directions carefully, but most likely they are not included in online homework. So if you were drawing the structure of ethanol, you would just write it out like this with no lone pairs. But especially at the beginning, I recommend that you draw out the lone pairs, especially because electrons do the reacting. So it's good to keep track of them, and then they affect formal charge, whatever. So right now, I do recommend that you show lone pairs when you're just practicing and when you're following along with lectures. Now that we can draw these skeletal structures, let's move on to thinking about what we can learn from them. I would pose the following question to you. Why do all of these molecules have a fruity smell? This first molecule is responsible for the smell of cherries. The second one, the smell of bananas. And lastly, this molecule is responsible for the smell of peaches. So why do all 3 molecules have fruity smells? What do you think? Write it down. All 3 of these molecules have this group of atoms in common. This group of atoms is referred to as an ester. And because each one of these molecules has an ester functional group, each of them has a fruity smell. What is a functional group? Well, a functional group is a group of atoms and the bonds that connect them with a predictable set of chemical and physical properties. You must memorize these functional groups. For example, if I were to show you this molecule, I would want you to look at it and to think, hey, look, there's an ester. Recognizing that there is an ester or that there is whatever functional group in a given molecule will allow you to predict its chemical and physical properties because the functional group has predictable chemical and physical properties. And that will help you tremendously as you consider phenomena in organic chemistry. So our goals are to be able to identify functional groups within a molecule, as I did for this ester at the top of the page. And second, and this will come later, so right now we're focused on goal number 1. Second, as we move forward through the course, we want to know the properties associated with each of these functional groups. Know or be able to predict based on other things you know. So right now, let's work on identifying the functional groups between a molecule, and then later, / the rest of this semester and the rest of your life, we're going to work on knowing the properties or building the skills and the chemical intuition to predict the properties of each of these functional groups. Oh, how bad could it be? How many could we possibly have to memorize? Well, here they are. I'll give you a moment to take a look. Ultimately, you will need to use flashcards or some other way to memorize these functional groups, but let's discuss them a little bit together now. We see we have alkenes and alkynes. So alk, as you may or may not know, means hydrocarbon. It means carbon and hydrogen. So you can see for the alkene and the alkyne, there's just carbon and hydrogen atoms shown. Ene means double bond. Ine means triple bond. And don't worry, I'm not going to break down every single part of the chart, just the highlights. Ane means single bonds only. I might have something boring like this. The reason that alkanes are not included in this chart is because technically they're thought of to be without a functional group. Just beneath alkynes, we have arenes or aromatic compounds. We will discuss these compounds in great detail in Chem 12B, but for now, I just want you to recognize the six-membered ring with alternating double bonds. This is the prototypical aromatic compound. And in fact, we talked about it. This was molecule A in our introduction to today's class. And we drew the resonance structures and talked about the bond links. So you need to recognize aromatic compounds or arenes. And they're derived from the six-membered ring with alternating double bonds. Commonly. Not always, but commonly. And right now, that's all you need to recognize. Moving on from hydrocarbons, you might notice that several of the functional groups involve a carbonyl. A carbonyl is a CO double bond. What the exact functional group is depends on what is bonded to the carbon of the carbonyl group. The squiggly lines that you see here and here just mean that there's something on the other side bonded to that carbon. We just don't know what it is. Let's zoom in. For a ketone, so you see the carbonyl, and there are two alkyl groups, two hydrocarbons bonded to each side of the carbonyl. For an aldehyde, there's one hydrocarbon and a hydrogen. For a carboxylic acid, there's a hydroxyl. And on the other side, either a hydrogen or a hydrocarbon right here. For an ester, there's an alkoxy group, so an oxygen bonded to a hydrocarbon. And for an amide, there's a nitrogen, and these groups can either be a hydrocarbon with carbon and hydrogen, or just a hydrogen. It doesn't matter. All of these carbonyl-derived functional groups are different, and you'll want to identify them. You'll want to be able to distinguish a ketone from an aldehyde, from a carboxylic acid, etc. So just recognize the carbonyl, recognize that CO double bond right here, and then take a minute and look at what's attached to it, and that will tell you what specific functional group it is. Acetals and hemiacetals, these are derived from aldehydes and ketones. Their carbonyl carbon is in disguise. What do you think they mean by that? Yeah, well, you can see that these carbons I'm circling in purple, they're making two bonds to oxygen, just like the carbonyl carbon does. Just that the carbonyl carbon makes a double bond to oxygen, whereas in the acetal or hemiacetal form, it's making two single bonds to two different oxygens. We'll talk much more about that later. But right now, I really want you to be able to recognize all the different carbonyl-derived functional groups. And if you recognize acetals and hemiacetals, awesome. If you don't, we'll get there eventually. but these here with just a carbonyl CO double bond, need to start recognizing them right away. Before we move on from the carbonyl-derived functional groups, let me introduce to you a shorthand. So sometimes you'll see R. R is nothing. R just means some generic alkyl group, a generic hydrocarbon. For example, sometimes ketones are represented like this. So there's the carbonyl carbon, and then there are two R groups. This is just another way of showing that they're alkyl groups bonded to the carbon of the carbonyl, just like we've represented here. But R is just a little more generic, so we could have just written R. It means alkyl. We'll take a look at two more, and then I will let you do the rest of the investigation and memorization yourself. I will point out what's indicated in red are the atoms and bonds that make up the functional group. So this makes up a thiol, for example. Let's look at the alkyl halide here. Alkyl halide, alkyl, R, and then some halogen. Typically, X refers to halogens, and fluoride, chloride, bromide, and iodine. We will most commonly encounter in this class chlorine, bromine, and iodine involved in it. X is generic for halide. If we wanted to specify alkyl bromide, then we would write RBR, and that would be an alkyl bromide. Lastly, we'll take a look at alcohols and phenols for just a moment here. A phenol is a special kind of alcohol. You can see both of them have this hydroxyl. They have the OH group and then an alkyl group, R. But in phenol, the R group is actually an aromatic compound. It's an arene, benzene to be specific. So phenol is a special kind of alcohol. You do want to try to recognize it because its properties will be just slightly different than normal alcohols. And that's why it's included in this chart from your textbook. So again, I could cite for you all the different types of functional groups and everything about them, but I need you to take a look and do that work yourself and ask me what questions you have, because it'll be super boring for me to promise you. It'll be very boring if I sit here and go there. This is an epoxide. You can do it. Let me know what questions you have. Have this chart out as we get to the hard part, which is the identifying functional groups in organic compounds. This is an example of a pharmaceutical agent called ditropan. I would like for you to circle and label the functional groups in this molecule. Pause and try yourself. We have an arene or an aromatic ring. We have an alcohol, which is an alkyl group bonded to a hydroxyl. So let's take a look in the chart. Arene, alcohol. So we have seen examples of both of those functional groups in this molecule. Now, this is where it gets tricky. We could say, oh, it's a ketone, it's a carbonyl. No, look at what's bonded. So here's the carbonyl carbon. It's your friend. You might as well start recognizing it now. You need to look at what is bonded to the carbonyl carbon. And then you can decide specifically which type of carbonyl derived functional group it is. So you can see that the carbonyl carbon is bonded to an O, here's the O, and then an R. And then on the other side, it's bonded to R. So that means, so carbonyl carbon bonded to OR and R, so an O alkyl and just an alkyl on the other side, that will correspond to an ester. Okay, or this is an alkyl group. And that's in contrast to a carboxylic acid, where instead of alkyl, it's a hydrogen. And those two functional groups are going to have pretty different properties. They'll have some things in common, but other things that are different. So we want to be able to tell them apart. So we would circle this entire group, and we would label it an ester. And there's an alkyne, this carbon-carbon triple bond. And this is specifically an example of an internal alkyne. So you could have your alkyne in the middle of a chain, internal. So it's in the middle of a carbon-carbon chain. Or you could have a terminal alkyne where the carbons making the triple bond are at the end of the chain. And you might say, well, why does that matter? Well, the terminal alkyne has this CH bond to the alkyne carbon, and that will have some special properties that we'll talk about. So, just pointing it out, internal versus terminal alkyne. And finally, we have an amine. Amines are nitrogen atoms bonded to either hydrogen or bonded to an alkyl group. So in this case, it could be R or it could be H, alkyl or just a hydrogen. So we can see that on our chart as well. It's right here. So we'll have one alkyl group at least, and then this could be hydrogen or R, hydrogen or alkyl. Because of course, if they were all hydrogen, then we would have what? We would have ammonia. Good. So I can guarantee you'll have a question on your first exam that involves circling and labeling functional groups. One more time, why does it matter? Why are you going to have a question like this on your exam? Well, because they help us to predict and understand the chemical and physical properties of a molecule. Recall that there are 70 million known organic compounds, and we do not want to memorize every single little thing about every single organic molecule. So what do we need to do? We need to look for patterns, and these functional groups provide the basis for patterns and reactivity, and we want to really rely on them so that we don't have to memorize a zillion different things. I can give you one more example. I showed you that some small esters smell sweet. We saw that at the beginning. They have those fruity smells. Well, another smelly functional group is the thiol. Thiols have an alkyl group bonded to an SH. This is the sulfur variant of the OH, so of the alcohol. So thiols are like alcohols, but they have sulfur instead of oxygen, and they are smelly. They smell awful, smell a little bit like rotten eggs. So ethane thiol, this molecule is very smelly. It is often an additive in natural gas or other chemicals where you need to be able to smell them if they leak. And then here's a pretty different example of a thiol. It has a 6-carbon ring instead of a 2-carbon chain. Well, guess what? It's smelly too. They're both very smelly. And I can tell you from personal experience, I've worked with both of those molecules. They smell awful. I think it can be somewhat straightforward to see functional groups in these small molecules, but as the molecules get a bit bigger, it might be a little more difficult. So let's pause again and identify the functional groups in cholesterol. What did we come up with? Well, we have an alcohol, an alkene, and then cholesterol is pretty boring after that. We just have this big alkane or big alkyl region. And even though this region doesn't have any functional groups, it still has some pretty important properties that we'll talk about later this week. Just for fun, I'll point out the 665 ABCD ring system of a steroid. Students often recognize this from their past classes. So cholesterol is a steroid. No, you don't need to know this. It's for fun. Okay, it's a steroid. It's a biomolecule. Your body is making cholesterol and other steroids right now. Awesome. Good job, body. Let's take a look at the functional groups in some other biomolecules. Here they are. And if you know what type of biological macromolecule it either is, represents, or it can be part of, write that down too for fun. Our first molecule, molecule A, this is an example of a carbohydrate. And specifically, it's a carbohydrate in its open chain form. This is glucose, and we've also seen glucose in its closed chain form. I believe we looked at it in our Introduction to Organic Molecules class. And this is how you would represent glucose in its closed chain form. So carbohydrates can either be in an open chain like this, or they can be closed up into a ring. So acyclic and cyclic. Looking at the functional groups in glucose, because both of these are glucose, we can see there's an aldehyde, and then there are many, many alcohols. In fact, it looks like every other carbon has an alcohol functional group on it. And that is not a coincidence. Carbohydrate, where does that name come from? Well, carbohydrates have a molecule of water for every carbon. Okay, so their formulas you break down to this usually. Now these are monosaccharides, and disaccharides you'll actually lose one of those molecules of water. So monosaccharide. But you know that disaccharides exist where two sugar units come together and make a bond, and polysaccharides. In the cyclic form of glucose here, we can see that we still notice the alcohols. But then the aldehyde functionality seems to be missing. It's not, it's just that the aldehyde is now an acetal, or it's a hemiacetal specifically. And I mentioned we're looking at the chart of functional groups that hemiacetals and acetals are related to aldehydes and ketones. So that's what you observe instead of an aldehyde in the cyclic sugar. And for fun, I can show you one more sugar. So we looked at glucose. Molecule A is glucose. We can also look at fructose. And I'll draw fructose up at the top of the page. And I would like for you to identify the functional groups in fructose. We still have a bunch of alcohols. What's different? Yeah, we have a ketone instead of an aldehyde. So you have a ketone instead of an aldehyde. This is a ketone because the carbonyl carbon, and you really might just start getting in the habit of identifying the carbonyl carbon. It's your friend. So the carbonyl carbon, the one that's double bonded to oxygen, in fructose is bonded to two alkyl groups, whereas in glucose, it's bonded to a hydrogen and then the alkyl chain, and so it's an aldehyde. Let's move on to molecule B. Do you recognize molecule B? Yes, molecule B is a peptide, and it's just a small protein. Proteins, of course, have many amino acid units. The peptide is just a couple. So this comes from amino acids. And amino acids look like this. You have an acid part, an amino part, and then some alkyl group usually. So this is called the side chain. But R actually can also be hydrogen. And then you have the amino acid glycine. But don't worry, we're not in Bio 60. You don't need to memorize all of that. The purposes of this exercise is just identifying functional groups. So we have a carboxylic acid. This is a different example of a carbonyl functional group, one we haven't looked at so far. And then you have what else? Yeah, you have an amine. Cool. So that's what we have in the amino acid. And then a bunch of amino acids come together and they make a peptide or a protein. Let's look at what we have in the peptide or the protein. So we still have amines on this end. We have an amine end. We have a carboxylic acid on the other end. Trying not to use my bio words, but I really want to. And then there's one more important functional group that we now have that forms when amino acids make peptides. Yes, it's an amide. Cool, so we have two amides there. Last biomolecule, C. What is this? Yeah, this is a nucleotide, and nucleotides make up nucleic acids like DNA and RNA. Many fun functional groups here in the nucleotides. So we have the phosphate. We have a sugar, a carbohydrate. Here it is. And whether or not this is DNA or RNA depends on that carbohydrate. And it depends on this carbon right here. The D in DNA stands for deoxyribose. The R in RNA stands for ribose. So in DNA, you're missing the hydroxyl on that carbohydrate, right? Because every carbon in the carbohydrate should have a hydroxyl. Look back at big glucose up here. Every carbon should have a hydroxyl. So if it's missing the hydroxyl, it's DNA. If it's just normal old ribose with all of its hydroxyls, then it is RNA. Finally, we have the nitrogenous base that makes up final functional group in the nucleotide. Okay, and check it out. We'll talk more about this in 12b, but hey, it's aromatic. There's some nitrogens instead of carbons, but that's definitely alternating pi bonds, so that's an arene. All right, look, you don't need to know all the details. Just want you to recognize the biomolecules. And then if they have functional groups that are on our chart, and many of these functional groups are on our chart, then you should be able to identify those functional groups. Am I going to ask you to identify a nitrogenous base? Probably not. But we can see the alternating pi bonds, right? Yeah, so we can see it's aromatic. That was fun. Let's move on. So let's take a look at molecule Z here. Look at some simpler molecules for a minute. Predict which of these molecules, 1, 2, 3, or 4, will have properties most similar to molecule Z. Take a moment, try this on your own. We can see that molecule Z has a carbonyl, and then there is an alkyl chain bonded on one side of the carbonyl. On the other side, there's a hydroxyl group. So this is a carboxylic acid. If we wanted to circle that carboxylic acid functionality, we would circle it like this. Now, to figure out which of these molecules has properties most similar to molecule Z, we should identify the carboxylic acid. Molecule 1 contains an alcohol. Molecule 2 contains a ding, 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 carboxylic acid. Molecule 3, it's a ketone, because we simply have R groups, alkyl groups, bonded to the carbonyl carbon. And then molecule C is an ester. So certainly the ketone and the ester will have some things in common, and so will the alcohol, frankly, with molecule Z. But what has most in common with it? The carboxylic acid. These carboxylic acids will have similar chemical and physical properties because they are determined in great extent by the functional group. Same functional group, similar chemical and physical properties. One more problem. Let's consider this molecule, molecule X. It contains a functional group that I did not ask you to memorize. However, molecule X behaves very similarly to a functional group that you are required to memorize and will encounter frequently in this class. So, which functional group do you think that is? Let's go to our table. Our table is messy. Let's zoom in here a little bit, and I will draw molecule X for you again. We'll throw its lone pairs for fun. So which functional group do you think that this behaves most similarly to? Well, it's called a sulfide, and a sulfide is the sulfur variant of an ether. Yes. So how can we make this prediction? Well, we have two R groups. And then, of course, sulfur and oxygen, they are both in group 6A. That's kind of why I drew the lone pairs in, to maybe jog your memory on that. So they're both in group 6A. So we know that in general, carbon and oxygen have similar chemical and physical properties. And when they're bonded to two R groups, that overall functional groups will also have similar chemical and physical properties. Not the same, but they're pretty similar. Good job. We are ready to revisit our learning goals and get to the practicing. Can we convert between bond line, aka skeletal structures, and complete Lewis structures? Yes, we can. So we know every end or bend is a carbon atom. So we have an end and a bend. So we have two carbon atoms bonded to an O and an H. We need to show all bonds. I have to write this bond out. I need to show the lone pairs as well for a complete Lewis structure. And then I fill in hydrogen atoms to complete the octet of each of those carbon atoms. These three hydrogen atoms, they were implied in the skeletal structure. Define functional group. Yes, this is a group of atoms that have characteristic chemical and physical properties. Can you identify or name them? Yes, you can do this, but you're going to need to memorize the functional groups, and you can make flashcards or do something else more creative if you would like to, but you do need to memorize this. Finally, classify a biomolecule as a protein, carbohydrate, or nucleic acid based on the functional groups. We talked about this here. I know I told you a lot of fun facts. Most of them were fun facts. What you need to be able to do is say, hey, this is a nucleic acid, or this is a nucleotide. Super. This is a peptide or a protein. Super. This is a carbohydrate. Great. And then if the molecules contain functional groups that we learned, functional groups that are from this chart, then you should be able to identify those functional groups as well. Finally, the very last step, do not skip it. It is critical to you learning and retaining this information. Be sure that you summarize and reflect. And I'm sure this class relates to many different things you've learned in previous classes, so this should be a fun question today. If you have any questions remaining, please contact me or please ask your group members. Now it's time to practice.